Everyone, my name is Matteo Gambara, and I'm going to talk about consistent recalibration equity models. This is a joint work with Joseph Teichmann, both from ETH Zurich. First of all, the motivation. We are introducing such models because we are basically unhappy with the current calibration procedure. Usually, we are simply writing down the SD for the model, then trying to match market observable prices with model prices. But this simple procedure has two problems at least. The first one is that to reproduce all prices, we might have to add new parameters or to increase the dimension of the state space. Second, after some time, we need to recalibrate thus to change again the parameters. But this is unsatisfactory from a theoretical point of view, since only the state variables are supposed to change. There are possible fixes. For example, Markovian models, which try to add unobservable state variables. For example, the Heston model, which is adding V, the instantaneous variance of the process X, or also HJM-type models. In this case, we are not modeling the underlying asset, but rather the codebook, which is a deterministic one-to-one map between the reference asset and derivatives prices. Think, for example, of the implied volatility in Black-Scholes model. In this way, we are directly modeling the liquid traded instruments together with the reference asset. And it is the basic assumption for all market models. We have to be careful with the choice of the codebook because then arbitrage conditions will depend on those. Drawbacks for Markovian models are the too low dimensionality, plus they are not robust and inconsistent over time. While for HJM-type models, we have that they are quite complex due to their high dimensionality. So basically almost the opposite of the first ones. CRC models try to stay in the middle, getting advantages of both models. We will have a codebook. Instantaneously, the model will look like a finite factor model, thus analytical tractability. And thanks to a revision of half height extension, parameters will be seen as state variables. So the codebooks, we will find or look for codebooks in this set gamma n, which is the collection of continuous function eta, our codebook, such that there exists a Cadillac process Z satisfying this condition. Another important condition is the so-called conditional expectation condition, or CEC, which is a martingale type condition for our tuple X eta. The process eta, so the codebook is called the forward characteristic process of X. The process kappa is called just the process characteristic of X, and it might or not coincide with the codebook at the initial time. And we also suppose that eta admits a regular decomposition with respect to a d-dimensional semi-martingale M, where alpha and beta, the coefficients, satisfy the appropriate integrability condition. The CEC is very important because it's equivalent to this. First of all, it is equivalent to these two conditions, in particular the HJM drift condition. This is basically a generalization of the most famous, of the more famous condition derived by Jerome and Morton in their seminal paper in 1992. Plus, it can be shown that the codebook is of Levi-Kinchin type for all times. And if the CEC is satisfied, then we are in a non-arbitrage market setting. In a simpler setting where X is one-dimensional, locally independent with respect to M, we can retrieve the well-known HJM drift condition, which was formulated by Jerome and Morton, indeed. Now let's talk about affine stochastic volatility models. And these are a subset of affine processes. X and Y represent the homogeneous affine process. X is responsible for example, represents the returns of the log prices, while Y, the stochastic covariance process. This is the definition. It's very important for us to get from this slide that they satisfy appropriate Riccati equations. Here, f and rc are two functions which are of Levi-Khinchin type, and f encodes the constant part of the process. We can indeed modify f, staying without quitting the class of affine stochastic volatility models, to include more information. And this is done with this generalized Al-White extension. It's called generalized because we're not simply adding a drift, a time-dependent drift, for example, as it was done in Vasicek model for the interest rates, but rather a Levi process. In this way, X will become time inhomogeneous, but we can still write explicitly our codebook in this way. You will see now here F depends on T. In this way, we are adding a lot of calibration power to our model. Indeed, we can somehow stay on the same volatility or price surface, but compensating changes in the parameters of the model with changes in the jumps of the same model, which are now introduced by this Levi process. To see an example in practice, we can start from the Heston model. These are the Riccati equations for the Heston model. For us, it's interesting, this F. And when we go to this generalized Bates model, we see we are modifying F. This first part was the same as the part of the Heston model. Kappa is a compensated cumulant generating function. And introducing this factor will also, as a consequence, the introduction of this Levi process for the returns of the underlying asset. Now we see that we can change at the same time the parameters theta, sigma, and rho, and the parameters of the jump process in order to stay on the same price surface. Calibration. Now, the calibration, the idea is to exploit, I wrote here implicit calibration because we exploit neural networks in two steps. In the first step, we are learning with the neural network, which will be called NN1 here, a map between the parameters of the model and the prices or the implied volatility surfaces. And then we are fixing somehow this neural network. We are aggregating to it another neural network called NN2. The composition of these two neural networks will form NN3, and then we let NN3 learning the identity. NN1 will be frozen, so then only the weight of NN2 are able to change. In this way, NN2 will be somehow forced to learn a map from the volatilities to the parameters. Learning does the inverse map that we should be able to learn every time we want to calibrate a model. This is the framework. Here are specified all the input and outputs for the different neural networks. As a side remark, it's important to say that we are able in this way to simulate for an indefinite amount of time an implied volatility surface which evolve remaining in a non-arbitrage setting. Here in red, this is the algorithm. In red, in green, there are the points where I used the neural network. And yeah, now I can show you the video. This is the volatility surface evolving in time. When some of the parameters change, then the parameters of the jumps of this stochastic Levi process are also changing, so that we stay on the same volatility surface. The problem of calibration is in this case ill-posed. It's quite difficult. It would be infeasible to use normal or traditional algorithms to solve it every time. That's why we need neural networks. And the HJM drift condition is fully incorporated in every step of this evolution in time. And thus we keep the volatility surface in a free arbitrage setting. Thanks a lot for your attention. And these are the main references.